Dams have been constructed of earth for thousands of years. Many of these early dams still exist. The Corps of Engineers builds earth dams where conditions are adapted to this type of construction and where suitable materials, soils, and rocks are near the proposed site. Earth dams are economical and efficiently fulfill the purpose for which they are designed. One of the major functions of an earth dam is to control floods, to prevent swollen rivers from paralyzing the industrial and agricultural life of a community, or destroying the property and even the lives of its inhabitants. Flood control diverts these destructive forces to beneficial uses. Also, earth dams aid river navigation by ensuring channels of sufficient depth for the passage of river craft. During periods of low water stages, water is released from the reservoir pool to maintain minimum channel depth. Another important purpose is to furnish the surrounding area with cheap hydroelectric power. These functions and many others call for very carefully engineered structures. The construction of a dam starts with the design. The engineers plan structures based on topographic data, foundation data, and hydraulic data. In appropriate cases, scale models are used to study the sequence of construction operations. When plans and estimates are completed, construction is awarded to private contractors on the basis of competitive bidding. However, the work of the engineers doesn't stop with design. Field forces supervise the construction to ensure adherence to the plans and specifications. Also, they continue exploration of the foundations and borrow pits to determine if they're required in the interests of safety and economy. An earth dam, in effect, is a man-made stream barrier retaining a reservoir of water on its upstream side. Roadways are often built across the crest of a dam, serving as a valuable traffic artery. In cross-section, a typical earth dam is a comparatively simple structure. Component parts that make up a dam will be studied separately, but first, let's look at a general plan. An earth dam may be founded on bedrock or overburden materials consisting of pervious or impervious soils. Where the overburden is relatively shallow, an impervious cutoff extending to bedrock is used as the principal seepage control measure. On deep pervious foundations, upstream blankets and downstream relief wells are used for this purpose. On each side of the central core, shells which are more pervious are designed for stability. On the reservoir or upstream side, the embankment is surfaced with a bedding or filter layer and a layer of riprap to withstand the wave action of the reservoir. On the downstream side, grass or other vegetative cover forms a protection for the embankment slope to prevent erosion from wind and rain. A pervious sand or gravel zone and a tow drain pick up and carry off water filtering through the foundation and the embankment. The first step in the construction on any dam is the clearing of timber, brush, stumps, and so on. Here a bulldozer is bucking such growth in piles. Steep slopes are broken down. Test pits and stump holes are filled in. These operations are to level the ground so that construction equipment can operate efficiently in the area. The piles of timber, brush, and stumps are usually burned. However, if the timber has salvage value, it is set aside for further use. Stripping comes next, the removal of vegetation, root mat, grass, peat, wet organic clay, muck, and other unsuitable materials. In this case, swamp muck is being removed with a clamshell bucket. Bulldozers blade away vegetation and topsoil. The purpose of stripping is to remove these soils from the upper part of a foundation, which are weaker than the foundation soils. Care should be taken not to overstrip the foundation. Overstripping would remove materials as strong as or stronger than the planned embankment fill. Ploughing and harrowing the foundation follows. This helps obtain a good bond between the foundation and the first layer of the embankment. This disc harrow is running in a direction parallel to the axis of the dam, which ensures a satisfactory bond. A cutoff trench reaching to bedrock or impervious soils is then excavated. It will act as a barrier to reduce to a minimum water seeping from the reservoir through the foundation and under the dam when filled with impervious material. For excavating the cutoff trench, a dragline bucket is one of the many kinds of excavating equipment used. During excavation, there is apt to be considerable seepage of water from the foundation into the excavation. To control this, a line of well points may be installed. These well points, arranged along a berm in the foundation, pump out the seeping water before it can enter the excavation. A well screen keeps out the soil, but permits the water to flow into the pipe. A well point is installed by jetting a hole into the foundation and setting the point into that hole. Then the well is connected in a line with other wells and linked into a discharge line. Even so, some of the water gets into the excavation. Therefore, a drainage ditch is dug out at the toe of the excavated slope. This allows placement of the cutoff trench backfill on a comparatively dry foundation. The excavation then continues into the impervious foundation to get a good seal between it and the trench backfill. Any excess water still left is removed from the base of the excavation before it is ready for the cutoff fill material. Impervious soil is now hauled in, dumped, and spread in thin layers. Wherever there are crevices or holes that can't be reached by machinery conveniently, the fill is tamped by mechanical means to level them out. Spreading in thin layers continues with constant inspections during placement of the fill to determine if the soil possesses the proper moisture content for compaction. A sheepsfoot roller is used for compacting the soil. It runs close to the sides of the excavation for good compaction against the excavated slopes. The tamping feet of the roller make it possible for compaction to take place below the surface. By repeated trips, a strip of soil gets thorough compaction. When the soil is at proper moisture content, the tamper foot, after a few trips, will penetrate the fill about half its length. If the moisture content of the soil is too high, the penetration of the tamper foot will be too deep, and the drum itself will rest on the fill. When the fill is too dry, the tamper foot will scarcely penetrate. On the downstream side of the dam, it is often beneficial to construct a tow drain in which a collector pipe may be incorporated. The purpose of such a tow drain is to pick up seepage through the foundation or through the core. Relief wells are used where deep pervious layers are present in the foundation. Filter layers are used to prevent movement or migration of the fines from the embankment or foundation through coarse or crushed rock of the tow trench. The collector pipe carries the seepage water away. In constructing the tow drain, a filter layer is first placed on the bottom and sides of the excavated trench. Pockets of coarse material or oversized rock in the filter layer are removed or distributed to ensure uniformity of the filter. A processing plant for pervious sand and gravel for the tow drain is set up by the contractor near the construction site. Its function is to remove the excess coarse and fine particles and then recombine the sizes left to obtain a desired gradation of material. The processed material is brought in and dumped. It is spread, keeping segregation to a minimum by proper manipulation of the bulldozer. Upon completion of the tow drain, the pervious drainage blanket is placed directly on the stripped foundation. Embankment materials come from nearby borrow pits. When this material is too dry, it is best to pre-wet it before it arrives at the construction site. One method for pre-wetting is by ponding. Water is pumped into these ponds and allowed to seep down over a period of several days or weeks to increase the water content of the soil. Another method of pre-wetting is the use of large sprinklers, known as rainmakers. Shovels are used for excavating soils from borrow pits, particularly where it is desirable to mix the materials during excavation. Elevating graders are also widely used where materials are uniform in character. Borrow pits should be located as near to the dam site as possible to reduce the hauling distance. Usually, pits are located on the upstream side. Then the excavations left increase the reservoir capacity. Material is next placed in the impervious core. This core acts as a barrier to reduce to a minimum water seeping from the reservoir through the dam. Bottom dump wagons are used to haul the impervious material. The soil is either friable, capable of being readily broken down, or chunky, as is the clay in this scene. The type of material going into the fill determines the type of processing equipment to be used. After dumping, the material is spread in relatively thin layers, which after compaction should be about 6 inches thick. If the soil contains large chunks, a special roller having cutter blades instead of tamping feet can be used to cut the material into a texture more suitable for compacting and rolling. large stones and cobbles are removed. No stones should be left that are larger in diameter than the thickness of the compacted layers. Methods used in removing stones depend on the rockiness of the borough material and the equipment available to the contractor. The soil is now ready for compaction. A sheepsfoot roller is used for this, running at about 2.5 to 5 miles an hour, making a specified number of passes over each strip. Weather is important during compaction. When rain is anticipated, a smooth roller is used to compact the surface on a slight grade so that rain will run off and not soak into the soil. Excessive moisture would delay the placement of additional fill. If, on the other hand, the soil is too dry as it comes from the borrow pit, it may be moistened at the fill by sprinkling it. Prior to the placement of the next layer of the fill, if the surface of the embankment is too smooth to permit a good bond, it is loosened up by means of scarifiers. Impervious soil may also be compacted with weighted rubber-tired rollers instead of sheepsfoot rollers. The individual wheel loads for such rollers vary from 15,000 to 25,000 pounds, with tire pressures varying from 70 to 90 pounds per square inch. A major problem is to obtain good compaction against steep abutments or against concrete sections. It is most important to slope the fill so that the rollers can get in close to compact a good bond. Whenever there is room for a sheepsfoot roller, it is used on the inclined slope as close to the steep wall as possible. Areas inaccessible to heavy equipment are compacted by mechanical hand tampers, building up a series of thin layers about 2 inches thick. The density of the hand tamped material should equal that of the material compacted by the roller. Compaction of a fill is under the constant supervision of inspectors. Before compaction, samples of fill material are tested to determine if the moisture content is correct for rolling. After the fill has been compacted, control samples are taken and tested to determine if the required densities are being obtained. A small area of compacted fill has been leveled off, and a hole is excavated into the fill by means of an earth auger. The hole is filled with dry Ottawa sand. The weight of sand used is obtained, and by means of a weight-volume calibration curve, the volume of the hole is determined. Material removed from the test hole is taken to a project soil laboratory, which on large projects may be portable. The moisture content and the dry weight of the material is determined to permit the computation of the in-place dry weight of the compacted material. Pervious soils make up the upstream and downstream shells. Where the core slopes are very steep, the pervious materials of the shells are brought up simultaneously with the impervious core to give it support. Materials for the pervious shells are composed of cohesionless sands and gravels. After dumping, the materials are spread to permit compacting in layers of specified thickness. The pervious fill is often compacted with caterpillar tractors. Sheepsfoot rollers can't be used satisfactorily on very gravelly soils. The tamping feet tend to displace the material instead of compacting it. Weighted rubber-tired rollers are well adapted for compacting such soils. On the downstream slope, a grass or vegetative cover provides for protection against erosion from rain runoff. Topsoil is brought in and dumped. Roots are removed. Bulldozers spread the topsoil on the slope. Spot sodding or seeding follows. The sods are placed by hand at close intervals. The downstream side of the dam is now protected against erosion from the elements. On the upstream side of the embankment, a bedding layer is placed on the slope and covered with a layer of dumped rock, known as riprap. This affords protection against erosion from the elements and the wave action in the reservoir pool. The bedding layer is composed of sandy gravel. It is dumped, spread, and compacted by bulldozers. It acts as a filter to prevent the removal of the embankment soils by the wave action, which penetrates into the voids or open spaces of the riprap. The bedding layer, in turn, is so graded that it will not be carried out through the openings in the riprap by the wave action. The riprap should be a firm, durable material which will not break down by weathering or wave action. It, too, is graded from coarse to fine so that the bedding layer material will not be carried through it. The size of the riprap is so selected that it will resist the tendency of the waves to move the individual stones and rocks. A complete record of the construction of finished earth dams is kept. Also, a file is maintained of field samples containing representative soils from various sections of foundations and many rolled earth dams have been built by the Corps of Engineers. Many are now under construction. Many are planned for the future. As long as threatening floods can endanger the lives and property of American citizens, the Corps of Engineers can be depended upon to carry out the directives of Congress in transforming these potential hazards to constructive forces beneficial to the public's interest.